In this video, we will discuss electrophilic aromatic substitution reactions, E, A, S. And yes, benzene does react. Electrophilic aromatic substitutions will substitute a hydrogen atom on benzene or a benzene derivative for some other species, which was an electrophile. Now, it doesn't happen in a single elementary step, so stay tuned and we'll talk about how and why it happens. The learning goals for this video are to be able to predict the products of electrophilic aromatic substitution reactions of benzene, draw the complete curved arrow mechanisms for these reactions, and propose synthetic routes to alkyl benzenes using reduction methods. So alkyl benzenes, substituted benzenes, some alkyl group. Let's get started. There are a number of reactions I'll be adding to your reaction chart. Before we get started on that, pause and predict the products of the following reactions. We always begin by identifying functional groups. If you haven't made any predictions, here I've given you some hints. Now please make your predictions. We know from Organic Chemistry 1 that alkenes react with bromine to generate vicinal dibromides. The anti-relationship of the two bromine atoms that are incorporated into the final product comes from the key intermediate of this reaction. In the first step, the pi bond acts as a nucleophile and attacks sigma star Br-Br. Filling sigma star Br-Br breaks the bromine-bromine bond. Now, bromine, molecular bromine Br2, has a good acceptor orbital, which is sigma star. It also has a good donor orbital, and that is the non-bonding electrons on bromine. And so those non-bonding electrons attack the empty pi star Cc orbital of the alkene. This elementary step leads to a bromonium ion, which is an electron-poor intermediate and behaves as an electrophile. When there are no other nucleophiles around, bromide, this bromide came from here, bromide will act as a nucleophile and attack the bromonium ion. It attacks sigma star Cbr in an SN2 reaction, which has to take place from the backside of the carbon-bromine bond. That stereochemical requirement for an SN2 reaction results in the anti-relationship between the new carbon-carbon bond that is made, this one, and the carbon-bromine bond that remains. Now, of course, bromide could have attacked either carbon-bromine bond, the one that was shown, or the one that did not show. And those two pathways, which are equally likely, result in a 50-50 mixture of the product shown and its enantiomer. So this 1,2 dibromide is formed exclusively as the anti-diastereomer, but as a racemic mixture. So we learned that alkenes react with molecular bromine or other halogens to generate these dihalides. We also learned in Organic Chemistry 1 that benzene is unreactive with bromine. So no reaction would be observed if benzene was treated with molecular bromine. As we know, benzene has a special stability. It's aromatic and unreactive under most conditions. We have studied this term. Think about it. If benzene had reacted with molecular bromine in the same way that is observed for a normal alkene, we might expect to see a product like this. However, where benzene is aromatic, possessing special stability, it's particularly low energy, this product, this dibromide, is non-aromatic. It certainly has a conjugated pi system, but overall it is non-aromatic and has lost the special stability associated with the property of aromaticity. And thus, this dibromide is not observed. Now, cyclohexene forms a vicinal dibromide when treated with molecular bromine. Benzene displays no reactivity with molecular bromine. This molecule, styrene, which has an arene conjugated to an alkene. These two carbons have p orbitals and are adjacent to one another, so this is an 8-atom, 8-pi electron system. This molecule, styrene, when treated with molecular bromine, does react, and it reacts at the alkene portion to preserve the aromaticity in the ring. When benzene is treated with bromine, and we just add one reagent, that reagent is iron 3 bromide. When iron 3 bromide is added to this reaction, an electrophilic aromatic substitution occurs. We can see that a hydrogen atom has been substituted with a bromine. What is so special about iron 3 bromide that all of a sudden benzene reacts with bromine? I'll answer that question in a minute, but one thing that we can notice right away is that the aromaticity in the product is preserved. This is still an aromatic molecule, it's just bromobenzene. That's one difference between what's happening here and what was proposed before, right? We said if benzene were to react with bromine as an alkene does, it would make a non-aromatic product, lose the aromaticity, lose that special stability. In other words, become higher energy. And that's not the case. So benzene can be forced to react with bromine, but when it does, the aromaticity is preserved. All right, let's figure out how and why benzene does react with bromine under these conditions. Well, the first thing that we can say, if we were to predict whether or not benzene would be a nucleophile or an electrophile, we would probably predict that, like an alkene, it will be nucleophilic. However, because the electrons in its highest energy occupied molecular orbital are so low energy, benzene is weakly nucleophilic. Right? The most reactive nucleophiles would have high energy electrons to donate. Benzene, these pi electrons, they're low energy. Recall the molecular orbital diagram for benzene. The three occupied molecular orbitals, pi 1, pi 2, and pi 3 for benzene are quite low energy. Pi 2 and 3 represent the degenerate highest energy occupied molecular orbitals for benzene, and they are low energy. So benzene is weakly nucleophilic. That's the point here. All of that said, benzene will react. It is reactive. It just reacts with very electrophilic species, so very high energy species. So again, benzene's weakly nucleophilic, and so we expect it to react with high energy, very electrophilic species. That leads us very nicely into the role of iron 3 bromide in this reaction. Molecular bromine interacts with iron 3 bromide in the following way. Iron acts as a Lewis acid. It has empty orbitals. And those low energy empty orbitals can react with bromine. Bromine acts as a Lewis base. It has relatively high energy non-bonding lone pairs. So bromine coordinates to iron. This elementary step looks familiar to us. We've seen coordination steps before for organic substances. Now, we predicted that benzene may react with high energy electrophiles, and that is exactly what has been generated here, a high energy electrophile. So what we'll have is this whole group here will serve as a stable leaving group. This will be a good leaving group. You say, well, I didn't know that. Well, that's okay. I'm telling you, and we'll see in a second. That's going to be a good leaving group. It's a stable compound when it leaves. And then this entire substance again represents that strong electrophile. Now benzene can donate pi electrons to sigma star BRBR. This is just like what we saw for the alkene with molecular bromine. Pi electrons donated to sigma star BRBR. But we're not going to have this counterattack here on pi star. That's really a main difference. That attack on sigma star BRBR breaks the bromine-bromine bond, and now, as we said, this entire group is a leaving group. This electrophilic addition step results in an intermediate that looks like this. Now, I've just drawn in the two implied hydrogens because it can sometimes be confusing for students what's going on. Now, this, of course, is a delocalized cation. We can draw several resonance structures. I was going to say I'll just draw one of them, but you know what? I'll draw all of them. So as far as cations go, this looks low energy because it's a delocalized cation, but it's non-aromatic, and that certainly required some energy. The step required energy to break the aromaticity of the ring. So this intermediate is delocalized. It's a delocalized cation, but it is non-aromatic, so it's still high energy relative to the starting material. And that's why this next step happens. So we saw an electrophilic addition to generate this cationic intermediate. And now this cationic intermediate will undergo electrophile elimination to generate the product. We have already seen that this hydrogen is replaced with bromine. So it is this hydrogen here that's going to be replaced with bromine. The hydrogen on the carbon that made the bond to bromine. So something needs to accept it. It leaves as a proton. I'm going to write SOL. That stands for solvent. That stands for solvent. That something accepts that proton. I don't like to have protons flying off here. So that generates that substitution product and the protonated solvent, whatever that solvent may be, probably some ether. Okay, so electrophile addition reactions, you have a pi electrons, nonpolar pi bond, make a bond to some electrophile. Okay, looks like this, make a sigma bond, break the pi bond. And then electrophile elimination steps, they regenerate pi bonds. So be sure that you review those elementary steps, electrophile elimination and electrophile addition. Because overall, we have a substitution, but it proceeds by those two elementary steps. All right, why is this reaction called an electrophilic aromatic substitution? Well, as we've said, there's been a substitution of Br plus, right? It didn't exactly add that way, but essentially that's what happened for H plus. And turns out this is going to be general for electrophiles, this mechanism, this type of transformation. As long as we can make a super electrophile, then this sequence will be, it'll be general. Yeah. We'll see it happen a couple times today. And I'll just repeat that. The aromatic ring here reacts as a nucleophile with an electrophile. So the electrophilic part refers to the species that's added. The aromatic refers to the benzene ring, and of course substitution, we've already been over that. Replace one group with another. I have good news and bad news. There are a lot of electrophilic aromatic substitution reactions. So it's bad news in that you need to memorize all these reagents, but the good news is they all, for the most part, go by the same generic mechanism. It's so nice when we can use patterns rather than just rote memorization. So there's going to be some electrophile, and oftentimes it must be generated. We saw here the electrophile wasn't either of these species. It was generated when they interacted with one another. So sometimes that electrophile is generated. But once it is, PiCC attacks it and an electrophile addition step, that is going to generate this stabilized intermediate. As you might imagine, since this electrophile addition step does generate a non-aromatic cation, this does represent the rate determining step for these aromatic substitution reactions. And then after that slow electrophile addition is the fast electrophile elimination step, or the solvent or some other species in solution accepts the proton, generating the final substitution product. And we can see the aromaticity is regenerated in that substitution product. So I'll teach you now how to affect each of these transformations. It's going to be super fun. We already have one down, right? To convert benzene to bromobenzene, the reagents are simply bromine and iron 3 bromide. And the active electrophile was that bromine iron complex. All right, so be sure that you have this down, you understand this, you understand this generic mechanism as it applies to the bromination, and then you're ready to move on. We're just gonna move on, we're gonna march through all of these reactions. We're gonna think about how this reaction can be pretty useful in synthesis problems, and then we're gonna be done. Easy peasy, right? Yeah, 2 hours later. No, it won't be that long. Okay, so go ahead and pause and write out the generic mechanism for electrophilic aromatic substitution as I have explained it to you, just to be sure we're all on the same page. We've discussed the bromination of benzene. Let's now discuss the chlorination of benzene. It occurs via a similar mechanism to the one discussed for bromination. Propose a mechanism for this reaction, then describe the similarities and differences compared to bromination. If you feel up to it, pause and give it a shot. Benzene doesn't react with chlorine. However, we see that there is aluminum chloride in this mixture. The first thing that happens is aluminum chloride, which is a Lewis acid with an empty p orbital, coordinates to chlorine. We don't typically think of molecular chlorine as a Lewis base, but it does have this lone pair of electrons that it can donate to aluminum.
This coordination step generates a very electrophilic species. Notice the positive formal charge on electronegative chlorine. This is very electrophilic. Now, benzene is weakly nucleophilic, but it's nucleophilic enough to react with this super electrophile. Pi electrons from benzene make a bond with chlorine. They're attacking sigma star Cl. That breaks the chlorine-chlorine bond, displacing what is a good leaving group. This electrophile addition step is the slow step in this reaction. Just draw in these implied hydrogens again so we're 100% clear about what's going on. The step is slow because it generates a stabilized but non-aromatic cation. I have drawn out these resonance structures because in our next lesson, it becomes important that you're able to do that. So you can practice drawing them out on your own as well. And I've just shown that the positive charge is shared between primarily the 3 carbons indicated, and the electrons are delocalized around the entire 5-atom pi system. Now, this non-aromatic cationic intermediate undergoes rapid deprotonation by the solvent. So we call that an electrophile elimination step since a pi bond will be regenerated. So the solvent deprotonates, reform the double bond here, and regenerate aromaticity in the product. This sequence of generating an active electrophile addition, followed by electrophile elimination, is consistent with the generic mechanism that we discussed before and that you wrote down in preparation for moving on. Let's review that generic mechanism one more time. For most of these electrophilic aromatic substitution reactions, the first step will be to generate the super electrophile, generate the active electrophile. Then there will be the electrophilic aromatic substitution part, which proceeds via 2 elementary steps. The first is a slow electrophile addition step, followed by a rapid electrophile elimination step, which in almost all cases, and not all, but I'll show you some practice problems where the electrophile that's eliminated is something different, but in most cases, and definitely for today, the electrophile that's eliminated here is a proton. So here I've diagrammed step 2, the important part, so the electrophilic aromatic substitution. And then, of course, before that can happen, the electrophile is generated. And these cations are stabilized by delocalization of charge. You should practice drawing the resonance structures. Let's go ahead and do that now. So this intermediate is stabilized by delocalization of charge and electrons, but it's non-aromatic, and more importantly, it's still a cation. So it is high energy, and this first step is a slow step. If we were to draw a reaction coordinate diagram for this process, we'd have a large activation barrier to generate this non-aromatic cation, followed by a rapid electrophile elimination with a low activation barrier. We'll apply this pattern over and over again. Just what E is varies. Let's see if this pattern applied to chlorination. First, the active electrophile should be generated, and that is indeed what we discussed for chlorination. Chlorine coordinates to aluminum chloride, which results in a positive formal charge on a really electronegative atom. This is certainly a super electrophile. Now, benzene can donate its pi electrons to sigma star Cl, breaking that chlorine-chlorine bond, relieving the positive charge on that chlorine, and making a new bond. Now, this is a slow step because it does generate a cation. And that cation is described by resonance structures. And you can draw those out, and you certainly should practice that. Okay, so all of that corresponds to this part of our generic scheme. And then now there is an electrophile elimination. Typically, because I do not like to just show the proton flying off here, I do invoke this solvent to accept that proton, because that is what happens. The proton does not just fly off into the ether, unless the solvent is the ether. Okay, so there's an electrophile elimination step generating that final product. And just keep all of this in mind, how the generic mechanism applies to each of these specific reactions that we learn as we continue forward. Let's add this to the little chart we have here. So generate chlorobenzene, there's molecular chlorine and aluminum trichloride. The active electrophile for this transformation, of course, was the complex between aluminum chloride and chlorine. Before we move on, we were asked to compare and contrast the chlorination reaction of benzene with the bromination reaction of benzene. And of course, one big difference is just the group that's being substituted for, right? It's bromine in the bromination and chlorine in the chlorination. Great. Well, why is that? Well, it's because the active electrophile is different. So this is the active electrophile in bromination, and here it is in chlorination. But it's made by the same way, right? There's some Lewis acid, so iron in the case of the bromination. And that's just because iron makes a nice strong bond to bromine. So iron is used for bromination, aluminum is used for chlorination, but in each case there's a Lewis acid used and then the molecular halogen. And the reactions proceed by the same exact mechanism. They both proceed by the same generic mechanism. Generate the active electrophile, and then electrophilic addition, electrophilic elimination. Excellent. Let's keep going. We will now look at the nitration reaction of benzene. So where a proton is substituted for NO2. I think that a good place for us to start is for you to draw out NO2. I've drawn out the NO2 group here, and it's important to keep that Lewis structure in mind. Now we see that for nitration of benzene to occur, it's treated with nitric acid and sulfuric acid, both very reactive acids. So this reaction must be conducted very carefully in the lab. The active electrophile for this transformation, the super electrophile, is actually the NO2 plus cation. And again, let's draw that out. All right, there it is. Following our general plan, which is to generate the active electrophile and then apply the electrophilic aromatic substitution pattern of electrophile addition followed by electrophile elimination, let's get started. So first things first, must generate the active electrophile. Now it clearly comes from nitric acid, so let's draw out nitric acid. And it looks like it's coming from this part, right? And that means that this needs to leave. Well, that looks like hydroxide. So does hydroxide usually leave? And especially under really acidic conditions, does hydroxide leave? No, it does not. It leaves as water, not as hydroxide. So the first step here, and I know this seems crazy, we're protonating an acid, but nitric acid is protonated by sulfuric acid. Whoa, nuts. Electrophilic aromatic substitution is so fun. This proton transfer step generates protonated nitric acid, which does now have this good leaving group water. It also has two adjacent positive formal charges and looks very unstable. Yikes, two adjacent positive charges. Yeah, this is a very high energy intermediate. Now, as weird as this may look to us, we do know, because I've told you that the active electrophile is NO2, and we can see how that's formed here. There's a lone pair push to generate the second pi bond in NO2+, and that will break this sigma NO bond, expelling water and generating the active electrophile. And it's simply a nucleophile elimination step, where the polar pi bond being formed will be the NO pi bond. Now that the super electrophile has been generated, weakly nucleophilic benzene reacts with it. As we have seen, there is an electrophile addition step of pi CC, this time on pi star NO, which breaks the pi NO bond and generates an intermediate that looks like this. This intermediate, of course, can be described by three resonance structures, which you should pause and try drawing on your own. The electrophile addition step is the rate determining step of this process, as it generates this high energy cation. To form the final product, this proton is no longer there, and this pi bond needs to be formed. The proton that's on the cationic carbon, that one is still there. Nothing happens to that proton. We'll invoke solvent to accept the electrophile that is eliminated in this step to generate the final product. This rapid step regenerates the aromaticity, and nitrobenzene is observed. If you reflect on how this mechanism fits in the pattern, what's different is generating the active electrophile. This is different from the bromination and the chlorination reactions. However, the electrophilic aromatic substitution is the same in that it proceeds via electrophile addition and electrophile elimination. We'll add this to our starburst. It's getting a bit busy here. Let's zoom in. Yeah, nice blurry slide. So for nitration, there's nitric acid and sulfuric acid. And the sulfuric acid is this there to generate the active electrophile. The active electrophile, of course, is NO2 plus, and I'll just draw it out. All right, we're moving along here. We have half the reactions done. We are going to move on to sulfonation now. So in sulfonation, a hydrogen atom is substituted for a sulfonic acid group. We have seen these sulfonic acids before. Often draw them out like that. So this is benzene sulfonic acid. You're used to seeing tosic acid, but we probably don't think too much about what it looks like. For tosic acid, instead of a benzene here, there is a toluene. So there's a methyl group on the benzene. And this is para-toluene sulfonic acid. Para because there is a 1,4 relationship between the two substituents on the benzene ring. Okay, we know these are really strong acids. So sulfonation is a way to make these strong acids, but you'll also see sulfonation is useful in synthesis. So that's why we're learning this reaction. Unfortunately, you won't get to see it used in synthesis until the next lesson. However, these are the two reasons why one would make a sulfonic acid. As a blocking group in synthesis, you'll see what that means later, or to make a strong organic acid. That's why we're learning this reaction. The overall mechanism will proceed via this two-step pathway where the electrophile is generated, the active electrophile is generated, and then there is an electrophilic aromatic substitution, where that electrophile adds to the ring, and then a different electrophile, usually proton, is eliminated. So the one that's generated adds, and then whatever was on the ring in the position that the electrophile added to, that is eliminated. The active electrophile in this reaction is SO3H+. Now, here's a little disclaimer. I will be drawing these sulfur and oxygen containing compounds like an organic chemist because that's what I am. The inorganic chemists would frankly be quite angry with me. However, this mechanism is just going to be easier if we do a little bit of pretend. And the pretending that I'm talking about here is that, look, really, these sulfur-oxygen bonds are not double bonds. There's not a lot of pi character in them. Sulfur and oxygen are in different rows. Their p orbitals do not overlap very well to make pi bonds. So these should not be represented as pi bonds, but I'm doing it anyways, and we're all going to have to deal with it. So if any of you go on in inorganic chemistry, I'm sorry. If any of you are inorganic chemists, I'm sorry. I just need to do what is easiest from the organic chemist perspective. Now, concentrated sulfuric acid contains sulfur trioxide. And oftentimes this is called fuming sulfuric acid. So if you see fuming sulfuric acid listed as a reagent, it just means that it contains sulfur trioxide. Some of that sulfur trioxide, which again, I'm going to draw like this because it's the easiest way to do it. Really, these are probably single bonds. I'm not going to talk about that anymore. So I'm going to show sulfuric acid protonating now the sulfur trioxide that is in solution. And the reason I'm showing that is because, heyo, that's the active electrophile. Now, this is quite reactive. We have a positive formal charge on oxygen. There's all those electronegative oxygens. This is a very electron poor species. So the super electrophile has been generated. With this electrophile, benzene will act as a nucleophile. And since this looks a little bit like a protonated carbonyl, I'm going to show it attacking as if it were attacking pi star. An electrophile is being added to the pi bond. The pi bond is breaking, so this is an electrophile addition step. For fun, one more time, we'll just draw in those implied hydrogens so that we can really keep track of what bonds are being made and broken, because sometimes that gets a bit lost, and I don't want you to be confused. We can draw all the resonance structures of this intermediate. There is the curved arrows to show the formation of the first resonance structure. And we can imagine one more resonance structure that describes this molecule. The composite resonance structure would look like this, where the positive charge is spread out over this 5-atom pi system. Following the slow electrophilic addition step is a fast electrophile elimination step, where the solvent deprotonates the carbon that now bears the sulfonic acid group, resulting in this product, this one.
As we mentioned at the beginning, this electrophile adds, right? So that's the electrophile that's doing the addition. And then in the electrophile elimination, I know it says E plus both times, but it's referring to a different E plus. It's referring to the proton, and that's on the same carbon that's making the new bond to sulfur, right? That carbon atom, we can trace that throughout as well here. This carbon atom here, it is undergoing substitution. And I just want to make that explicit a couple of times to make sure that some confusion is avoided. Wonderful. Now we know how to make sulfonic acids from benzene. We can add that reaction to this graphic. Concentrated or fuming sulfuric acid can be added to benzene to generate benzene sulfonic acid. The active electrophile in this reaction was protonated sulfur trioxide. Two more electrophilic aromatic substitutions to go, and then as mentioned, we'll talk about what can be done with these acyl products in a synthetic context. It makes sense we'd spend more time on these two reactions because these two reactions generate carbon-carbon bonds, and organic molecules are made out of, yes, carbon. So we're excited to learn about the Friedel-Crafts alkylation and acylation reactions. We'll begin with the alkylation reaction. As the name suggests, an alkyl group R will be added to the benzene ring. First, generate the superelectrophile. What do you think that will be in this case? What is a really electrophilic source of carbon? Well, there are many electrophilic sources of carbon. There are alkyl halides and tosylates. There are epoxides, carbonyl compounds. Any other ones? Well, those are the neutral ones. Maybe you thought of another one. I'll put a question mark there. Well, I think that's quite enough suspense. The conditions under which Friedel-Crafts alkylation, this is a named reaction because it is very important to making carbon-carbon bonds. And believe it or not, I know it looks kind of boring here, but these substituted aromatic compounds, they're pretty important in all different areas of chemistry. Okay, these conditions look a bit like this. So here's a specific substitution reaction. So this is a specific R group that we're adding. That R group is introduced through an alkyl halide. So I'll just use an alkyl chloride. But that's not enough. So if just imagine it. I mean, if you would you predict that if you mixed benzene with an alkyl halide, it would react? I don't think that you would, right? If we didn't see benzene react with, say, just bromine or halogen, those species were not electrophilic enough to react with benzene. And an alkyl halide on its own is not electrophilic enough to react with benzene. So in fact, none of these electrophiles are reactive enough that just benzene will add to it. But there's one more source of electrophilic carbon we didn't think about, and that's cations, carbocations. Whoa, these are high energy electrophiles. They're really reactive. So a carbocation is the superelectrophile for alkylation. To generate that carbocation quickly and quantitatively, we actually use our old friend, aluminum chloride. So we use a Lewis acid. Let's go through this mechanism now. So step one is generate the superelectrophile. And you might expect that this happens very similarly to what we saw for aluminum chloride reacting with molecular chlorine. There is a coordination step where that lone pair on chlorine can donate to the empty p orbital on aluminum. This generates a good leaving group. Chloride was already a good leaving group on its own, but now it's really a good leaving group. If this bond breaks, then that positive formal charge on chlorine will be relieved, and that's indeed what happens. So now this whole group leaves in a heterolysis step. And although this cation is relatively stable for a cation, right, it's tertiary, it is still high energy. So it represents the superelectrophile. Benzene will act as a nucleophile, as we've seen, in an electrophile addition step. Yeah, so benzene's acting as a nucleophile, but it's reacting with an electrophile. So this is called an electrophile addition step, where that electrophile that is adding is the cation. One of these carbons will make a bond to the carbon from the carbocation, and then the other carbon will be bearing that positive charge. It'll be the cationic carbon. We do know that that positive charge is spread out over all 5 of these atoms in the conjugated pi system. Now this time I'm not going to draw out all resonance structures, but you should be able to do that. So this cation is described by 3 resonance structures, one of which is this one. All right, so on the electrophile addition step, the carbocation added. Now there is an electrophile elimination step, and that step where the solvent removes this electrophile, H plus, and regenerates this carbon-carbon bond. And this net substitution reaction that proceeds via electrophile addition and electrophile elimination yields an alkyl benzene. Really exciting, a carbon-carbon bond has been made. This one. All right, this is a very important reaction in organic synthesis, but there will be some limitations to this reaction. What do you think those limitations are? Take a moment and write down what you think. Why might this reaction be difficult or not very general? Think for a minute, write down your answer. The active electrophile in the Friedel-Crafts alkylation is a carbocation. And thus, so this reaction will require a carbocation that does not rearrange in order to yield the desired product. We can look at a couple examples. Let's imagine that the following alkyl benzene is desired. This product reminds me a lot of the product on the previous page. Now we're imagining making this bond, and so that would come via this carbocation. This carbocation is tertiary and delocalized, right? This is a 7-atom pi system. So this carbocation is relatively stable for carbocations. The reagents for this transformation would simply be the alkyl halide that corresponds to this cation, so that would give that cation after heterolysis of the carbon halogen bond. Now, alkyl chlorides can be used, as we discussed, with an equivalent of aluminum chloride, or alkyl bromides with iron tribromide also work. So just like in the example that we looked at on the previous slide, where a carbon-carbon bond to a tertiary carbon was made, right? This carbon is tertiary, and so a tertiary alkyl halide was used, and a tertiary carbocation intermediate was generated. So just like with this example, this reaction would proceed fine. However, imagine that this alkyl benzene was desired instead. Now, this is the carbon-carbon bond that is made, and the following cation would be proposed. This one, right? So there's an implied hydrogen here. We can put that in. This is a secondary cation, which we know is not the highest energy type of cation, but that secondary cation is adjacent to a tertiary carbon. So we know that this cation will rearrange, and it will do so in a hydride shift. We can draw the curved arrows like this. So sigma CH migrates to the empty p orbital, and that happens because a tertiary lower energy cation is observed. So although we might propose treating benzene with this alkyl chloride and aluminum chloride, which will certainly generate this cation initially, the rearrangement will happen very quickly and the desired product will not be observed. Instead, the observed product will result from reaction of the tertiary cation. So we'll have an undesired product here. So to answer the question, what are the limitations of the Friedel-Crafts alkylation? Those limitations are it requires a stable carbocation that will not rearrange. or if it does rearrange, it does so in a way that is desired, that will lead to the desired product. Well, does that mean that this product can never be made? No, no, that's like never the answer, right? No, it just means, okay, we're just gonna need a new reaction for that. And I have one. Before we do that, let's add Friedel-Crafts alkylation to the starburst. Zooming in, the alkyl benzene can be generated from benzene using now an alkyl halide, so either a chloride or a bromide. If the chloride is used, then aluminum chloride is necessary to make the carbocation. If the bromide is used, then iron 3 bromide is required to generate the carbocation. And then, of course, as I'm saying, the active electrophile is a carbocation, and it must be stable and not rearranged. Excellent. One more reaction to go. I bet this reaction is going to solve the problems with the Friedel-Crafts alkylation. And speaking of problems with the Friedel-Crafts alkylation, we've actually only even described one of those problems. That first problem is that it requires a stable cation that will not rearrange. There is a second problem, and this second problem is of over-alkylation. It should remind you of when we tried to propose SN2 reactions with amines and alkyl halides, but the amines just kept getting more electron rich and they kept reacting and reacting and reacting. A similar thing is happening here. Let's imagine that we treat benzene with terbutyl chloride in the presence of aluminum chloride. This reaction does generate an alkyl benzene, but this alkyl benzene is still in the presence of the reaction conditions, and we know that alkyl groups are electron donating groups. So alkyl groups are our electron donating groups. This happens through the sigma framework. It's called hyperconjugation. We saw it when we talked about why more substituted cations are more stable. This is an example with a carbocation because it's easier to understand. But for a carbocation, we've said that tertiary is more stable than secondary, is more stable than primary. And that's because neighboring alkyl groups, imagine that this is a CH3 group adjacent to a carbocation. Neighboring alkyl groups can donate electrons to the empty p orbital in the cation. Just for a minute, sigma CH overlaps a little bit with the p orbital on the carbocation carbon, and then free rotation takes over, and that donation, ends until it aligns just for a second. And by second, I mean like picosecond, femtosecond. But it aligns just enough for long enough that this electron donating effect of the alkyl group does stabilize the carbocation. A similar phenomena is happening here to hyperconjugation. So alkyl groups are electron donating groups through the sigma framework. The effect is called hyperconjugation. And a consequence of the fact that the alkyl benzene has this electron donating group on it is that it is an even better nucleophile than just benzene. And so it's possible that the alkyl benzene is further alkylated to generate over-alkylation products. And although this product looks kind of cool, if this process is not desired, then this is a limitation of the Friedel-Crafts alkylation. All right, 2 limitations. Number 1, it requires a stable cation. Number 2, over-alkylation can happen. But, if you're careful, sometimes this can be avoided. Let's learn a different reaction that solves this problem. That reaction is the Friedel-Crafts acylation. Recall what acyl means. This is an acyl group. So how can a hydrogen atom or proton on benzene be substituted with an acyl group to generate a ketone functionality? The overall process might look like this. I'll just pick a specific acyl group. And often when you see the generic reaction, it might be written out like this, but I have chosen a specific R group. Here is the bond that's made in both the generic scheme and a specific example. All right, ketone is generated from benzene. Well, yes, it will proceed via the same 2 processes. We will need to make some super electrophile And then an electrophilic aromatic substitution will occur. That electrophile will add, and then the hydrogen atom will be eliminated. To generate that electrophile, then it adds, that'll be this acyl group, and then the hydrogen will be eliminated. It is an overall substitution reaction. Now, I will tell you that the ketone functional group comes from an acid chloride. But if we mixed up benzene and an acid chloride on its own, they would not react. Historically, benzene was used as a solvent until chemists realized how carcinogenic it was. So benzene, I mean, it is really inert. Until today, you didn't even know benzene reacted, right? It's inert under normal conditions. So it doesn't just react with an acid chloride. We need to take that acid chloride, even though it is really electrophilic, right? There's a nice big partial positive on that carbonyl carbon. It needs to be made even more electrophilic in order to react with the very weakly nucleophilic benzene. Similar strategy to before, we're going to add this strong Lewis acid, aluminum chloride, to the mix here. And aluminum chloride is going to coordinate with the chlorine atom of the acid chloride. You might be saying, what? Yes, I agree. It's shocking, but aluminum has an empty orbital, and electrons filling up empty orbitals, especially low line orbitals like the one on aluminum, that p orbital, there's a driving force for that. So yeah, I agree. Chlorine is not very Lewis basic in this context, but this reaction occurs. As one might imagine, this is a pretty high energy intermediate. There's a positive formal charge adjacent to an atom that has a partial positive. We have a lot of electronegative atoms here, and this is a high energy intermediate. What happens next might shock you. This is like a leaving group into the carbon-chlorine bond, so the bond between the carbonyl carbon and chlorine, it can break in a heterolysis. That heterolysis generates an intermediate that looks like this. It can be described by two resonance structures, and it looks like it's pretty high energy, and it is. But that's what's necessary for reactions with benzene, right? High energy intermediates. So this species is the superelectrophile. It is an acylium ion. Acyl, right? And then the ilium, because it has a positive formal charge. So this is an acylium ion. It is stabilized by delocalization of charge between carbon and oxygen, but it is high energy, and it looks high energy. Trust your chemical intuition here. Now generate the superelectrophile. Check. I think we've done that, right? This is the superelectrophile. Now that superelectrophile will react with weakly nucleophilic benzene. Here it is. So pi electrons from benzene attack pi star CO and displaces electrons onto oxygen. Now technically this would be reversible, but in practice, acylium ion is really high energy. In practice, this step is really not reversible. This delocalized cation is formed from the electrophile addition reaction. And just because I really want to stress to you today how important it is for you to draw resonance structures, even though we're not doing much with those resonance structures today, we'll be doing a lot with them later. So please be sure that you can draw the curved arrows to form all of the resonance structures of this non-aromatic delocalized species, because it becomes really important when we start to talk about the interesting reactions, which are to benzene derivatives. I mean, benzene's great, but oh, it's a bit boring. So we're gonna look at these same reactions again with benzene derivatives. And being able to draw these resonance structures will really help you understand what's going on with those reactions. Okay, slow step, electrophile addition, and now quick electrophile elimination to form the product. The electrophile that is eliminated, though, is proton, and the solvent facilitates that. This is the Friedel-Crafts acylation. It's similar to the Friedel-Crafts alkylation with a couple of differences. So let's talk about that now. How can we use the Friedel-Crafts acylation to avoid some of the problems with the alkylation? Well, recall what those problems were. There were two problems. There was the stable carbocation issue, and then the issue of overalkylation. So that once the alkyl benzene was formed, because alkyl groups are electron donating groups, The product was a better nucleophile than the reactant, and it kept reacting to form these overalkylation products. And overalkylation, because we're assuming that only one R group, incorporation of only one R group was desired. Now, it's easiest to address concern number 2 first, so that's what we're going to do first. In the Friedel-Crafts alkylation, as we said, an alkyl benzene is the product. In the Friedel-Crafts acylation, a ketone, an acyl benzene, is the product. Alkyl groups, as we said, are electron donating groups. Thus, this product is a better nucleophile than the original starting benzene. On the other hand, acyl groups with that carbonyl, acyl groups are electron withdrawing groups, both through the sigma framework because there's an electronegative atom, but also through the pi framework. We can draw resonance structures where some of the electrons in the ring are delocalized into the carbonyl. There are 2 other resonance structures that you can and should draw. What we see from the resonance structure that I drew is that this ring is less electron rich than just benzene without any substituents. So it is a worse or a less reactive nucleophile. So it's less electron rich, right? We see that positive charge in the ring than the starting benzene. And so we do not expect this molecule, this product, to compete with benzene as a nucleophile. So there is no overacylation. The product is actually less reactive than the starting material. Problem number 2 solved. All right, problem number 1. Let's imagine a synthesis problem in which benzene is the given starting material and the desired product is an alkyl benzene, such as this one. Someone may propose a Friedel-Crafts alkylation process to form this product. However, this would proceed via a primary carbocation, which is high energy and would certainly rearrange to form secondary cation at carbon 2. So this reaction is not a reasonable way to produce this product. Well, how does the acylation solve this problem? Well, let's take benzene and treat it with a 5-carbon acid chloride, because ultimately we're attempting to integrate these 5 carbons into the product to make this carbon-carbon bond. This ketone product would be formed from this acylation reaction. Now, of course, that's great. We added 5 carbons, but the desired product was the alkyl benzene. This was the desired product. So now the ketone must be reduced to generate the alkyl benzene. Do we know how to do that? What do you think? Do we know the reagents to convert the ketone to the alkyl benzene? Oh, we do. Not directly yet, but we do. We do. So we could reduce the ketone using lithium aluminum hydride followed by a dilute aqueous acidic workup to yield the secondary alcohol. Right? That is one way that we know of to reduce ketones. And although an alcohol is not the desired product, we can keep moving on from here. So there's no oxygen on carbon 1 in the product. We need to get rid of that. No problem. An elimination reaction can be used to do that. E1 elimination of the alcohol using concentrated sulfuric acid would yield an alkene. The alkene can be hydrogenated to the desired alkyl benzene with palladium on carbon and hydrogen gas. In summary, the Friedel-Crafts acylation does solve both problems with the Friedel-Crafts alkylation. Okay, give that a little bit more thought. Listen to this again if you need to, and we'll continue to talk about the Friedel-Crafts acylation. We are going to take a moment to answer some practice problems before we move on and finish up this lesson. In this first transformation, we identified that this carbon-carbon bond is made. We can see that there is an alcohol functional group in the product, which could be easily derived from a ketone. We do know our 2 options for generating that key carbon-carbon bond are either Friedel-Crafts alkylation or Friedel-Crafts acylation. And acylation seems to fit pretty well here because the alcohol can be easily obtained from the ketone. Now that we've chosen Friedel-Crafts acylation for our key carbon-carbon bond forming step, we know that that group indicated in yellow comes from the acid chloride. Aluminum chloride is required to generate the active acylium ion. This ketone is the intermediate of step 1. To convert the ketone to the alcohol, a reduction reaction must occur to add hydride to the carbonyl carbon. That can be accomplished with either sodium borohydride or lithium aluminum hydride. I will show lithium aluminum hydride here, but sodium borohydride in the presence of an alcohol solvent would have been perfectly acceptable. In the second reaction, there is no functional group on the benzylic carbon. We haven't used that term in a while, but that's the carbon adjacent to the phenyl ring. And it's the carbon that would be the carbocation carbon if a Friedel-Crafts alkylation were to be used. Now, certainly it would be easiest for this transformation to use the Friedel-Crafts alkylation since, again, there's no functional group on that benzylic carbon. So if we use the acylation, we'd have to reduce it and hydrogenate all of that like we looked at here. And you know, this was a lot. So if we can avoid that, that would be ideal. And in fact, this cation is secondary, but it is stabilized as it is conjugated to the adjacent phenyl ring, right? That's the benzylic position. So there are resonance structures that can be drawn to indicate how the ring stabilizes that carbocation. I'll just draw one of them here, but there are two others, and I certainly encourage you to draw them out. Because this cation is stabilized and not prone to rearrange, Friedel-Crafts alkylation is an acceptable route to the desired product. The carbocation does come from an alkyl halide, either an alkyl chloride or an alkyl bromide. You can number your carbons to be sure that you've chosen the appropriate alkyl halide. When an alkyl chloride is used, aluminum chloride should be used as well. If an alkyl bromide is used, iron 3 bromide is used. Now that we've practiced recognizing how to use both the acylation and alkylation reactions in box problems, let's do two things. So first, let's just add acylation to our starburst. Here we are. All right, this bond is being made, and this acyl group comes from an acid chloride. Aluminum chloride is necessary to generate the active electrophile for this transformation, which is the acylium ion. Yikes, that looks high energy. We've added it to the starburst. And now I'd like to continue discussing this idea that the Friedel-Crafts acylation is good for making alkyl benzenes that could not be made via Friedel-Crafts alkylation. For example, a generic alkyl benzene like this one could not be made via Friedel-Crafts alkylation. The alkylation proposes this primary high-energy carbocation that would certainly rearrange. Alkylation will not be a viable pathway. However, Friedel-Crafts acylation with the comparable acid chloride instead of the alkyl halide, the alkyl chloride, will in fact yield a ketone that can be reduced to form the alkyl benzene. That is, in fact, the largest challenge in making alkyl benzenes via Friedel-Crafts acylation. Alkyl benzenes don't have carbonyls, right? So that carbonyl should be reduced away. Well, we already know one method of converting a ketone to an alkane. I actually wrote it out for you just a few minutes ago. Let's pause and you write it out again and see if you remember that set of steps. Well, this overall reduction process takes place by two different reduction reactions. So the first is the reduction of the ketone to an alcohol using either lithium aluminum hydride or sodium borohydride to generate the secondary alcohol. That first reduction step accomplishes adding one of these hydrogen atoms that are found in place of the carbonyl in the alkyl benzene. The second reduction will actually occur to an alkene, so we'll add H2 across an alkene. To make that alkene, there's first an E1 elimination reaction of the alcohol and a hydrogen on the beta carbon, beta to the alcohol. This E1 elimination does take place via carbocation, so just be sure that the carbocation that you propose is stable, it doesn't rearrange and all of that. And if it does, use E2. It would just be more steps because you first convert the alcohol to a good leaving group and then eliminate with a strong base. Finally, that second reduction takes place with hydrogen gas in the presence of a palladium on carbon catalyst. So to actually add H2 across both carbons of the alkene. Of course, there are other fun reactions that can be applied to the ketone that will eventually generate an alkene or an alkane. You could imagine a Wittig reaction to generate an alkene, which could also be hydrogenated to an alkane if that was desired. All right, so that might be fun. So this process for reducing the ketone to an alkyl benzene did require a minimum of 3 steps: reduction, elimination, reduction. And then there could be more steps if an E2 needed to be used, for example. So let's learn a few other reduction techniques quickly for converting acyl benzenes into alkyl benzenes. And the whole point of this is that now you're able to use the Friedel-Crafts acylation to really make any alkyl benzene desired, just depending on what reactions are coupled with it. Well, the Clemmensen reduction is a method for removing a ketone from products of the Friedel-Crafts alkylation reaction. And I will just make one point. So the Clemmensen reduction should only be used with aryl ketones. This is an generic aryl ketone, right? And that's in comparison to this reduction method we already knew. This is more general. Again, you do have to be careful in that elimination step, but this is a more general method for reducing the ketone that doesn't have to be used with an aryl ketone. Although I did give an example of an aryl ketone there, acetophenone. So the Clemmensen reduction should be used exclusively with aryl ketones, and it occurs under acidic conditions in the presence of a metal reducing agent. So that reducing agent could be zinc, and that zinc is a mixture with mercury, so it's called an amalgam. It's pretty cool. And so this is just going to donate electrons. So this reductant is just going to donate electrons, and the protons and the hydrogen atoms in the product are going to come from HCl. The zinc amalgam is going to donate the electrons, and then the protons are going to come from the HCl. This reaction takes place under reflux, which means a boil, and that is considered pretty forcing conditions. Boiling in HCl, yeah, forcing conditions. So again, this is nice. It's a one-step reduction. So let's write a pro-con list here. Okay, one-step reduction. Great. Cons. It can only be used for aryl ketones, but that's great if we're talking about products of the Friedel-Crafts acylation because they're all aryl ketones. And it should be avoided when the molecule contains acid-sensitive functional groups, since it's conducted in boiling acid. For example, either the ring itself might have some other substituents, or the R group on the aryl ketone, if they contain alcohols, acetals, or any other functional group that's reactive with acid, then you should avoid this reduction method. Oh, what can I do? Well, you can do this one, or you can do the other ones we're about to learn. All right, you'll never draw out the curved arrow mechanism for this reaction, so don't worry about that. It proceeds via single electron chemistry, so a radical reaction. One more thing I'll point out though, sometimes iron is used instead of that zinc mercury amalgam, but there's a metal and it's in refluxing acid. Let's look at another method. That method's called the Wolff-Kishner reduction. Unlike the Clemmensen reduction, the Wolff-Kishner reduction is conducted under basic conditions. It is a two-step reduction, and as you can see, it's not specific to aryl ketones. Here I have an aliphatic ketone, that just means sp3 carbons. It is a two-step process. In the first step, a hydrazone is formed. The hydrazone looks like an imine, but instead of an R group here, there's an NH2 group. But this first step goes by a mechanism that is identical to that of imine formation. And I will not be drawing that mechanism out on this video. Are you responsible for it? Yes, of course, we've already learned the imine formation mechanism, and I can refer you to that video. Now, in the second step, that's where the reduction is happening. You can see that the carbon that was the hydrazone carbon, it ends up with two hydrides instead of that double bond. to nitrogen. So certainly there is a reduction there. And nitrogen is formed as a good leaving group. Now, although you could certainly understand the mechanism for this reaction, you definitely could. I'll just tell you, hydroxide deprotonates the amine hydrogens, and then the carbonyl carbon gets these hydrogen atoms from water in the form of protons. You can try this mechanism yourself if you want. You can ask me, I will show you. For the sake of time, I'm not going to write this mechanism in the video, but you could definitely figure it out. So really, we just need to know the overall transformation. Now, what are the pros for this process? Well, it can be used for a variety of ketones, not just aryl ketones. So just first generate the hydrazone under the same conditions that are used to form amines. And then the hydrazone is treated with KOH to form the alkene. So it's pretty general. Okay, the cons are that it cannot be used with base-sensitive functional groups. Right, for example, if there was an alkyl halide around and you treated it with KOH, well, we're going to see an elimination reaction. So if the ketone has an alkyl halide or some other base-sensitive functional group, you want to avoid the Wolff-Kishner reduction. But otherwise, it's really great for removing carbonyl. So although it does have a wide scope of ketones that can be used in this two-step process, for aryl ketones, the whole process can be conducted in one step. Now, it still goes via the hydrazone. Hydrazones, like amines, are best formed under mildly acidic conditions. For aryl ketones, though, the hydrazone can be formed under these basic conditions. You do have to heat it. So this is going to form the hydrazone. And then the KOH is going to eliminate nitrogen from the molecule by, again, deprotonating these hydrogens, and the electrons in those NH bonds we use to make a triple bond here. The electrons in these bonds will accept a proton from the water, AQ. If you want to write it out, you certainly can do so, but I will not require that of you. Okay, and then this is nice because it's a one-step process. But again, if you imagine that there's some other functional groups either on the aromatic ring or somewhere else in the ketone, you need to be careful that whatever those groups are not sensitive to base when you're heating this reaction. So it's forcing. All right, so for aryl ketones, there are two one-step reduction reactions with Wolff-Kishner under basic conditions, and then the Clemmensen reaction under acidic conditions. You would choose which method to use, really depending on what other functional groups are in the aryl ketone. Now, finally, the last method for removing carbonyl groups goes via what is called a thioacetal. So we'll talk about this a little bit, and then we'll cut to the chase because it's a long video. So when a ketone is treated with a strong acid catalyst, such as tosic acid, terephthalic acid, sulfuric acid, strong acid catalyst, in the presence of a dithiol, such as this one, these are thiols, and there's two of them, so a dithiol, a cyclic thioacetal will be observed. I would encourage you to try to draw the structure of that thioacetal. You're making an analogy to when catalytic acid in the presence of a diol is used to generate a cyclic acetal. All right, here it is. This thioacetal is formed by the same mechanism that acetals are formed by, which you are already familiar with. So yes, you're responsible for it, but we are not going to discuss it right now. All right, why are we talking about this? Well, we are talking about this because thioacetals undergo a really interesting transformation. They can be used to reduce carbonyls. So this time we're going to imagine using catalytic strong acid and just a normal thiol to generate, this time not a cyclic thioacetal, but an acyclic thioacetal like this. And of course, this same transformation would work if we had used the cyclic acetal from the previous question. This next reaction will yield the same exact process. So when any thioacetal is treated with a special metal, it's called rainy nickel. It's been treated in a really specific way. When those thioacetals are treated with rainy nickel in the presence of hydrogen gas, oops, sorry, I did not have that on the slide. Raney nickel is acting as a catalyst. What happens? What happens is that the sulfur carbon bonds are hydrogenated off. They are replaced by carbon hydrogen bonds. Whoa, crazy. I agree. And what's cool about this is that it is a general way to remove the carbonyl group, right? It doesn't just have to be aryl ketones. So you can imagine, let's say we take this aldehyde. I don't know why we'd want to do this aldehyde, but okay, we're going to take that aldehyde. We're going to add the dithiol with an acid catalyst and generate now the cyclic thioacetal. Treat it with hydrogen gas in the presence of this Raney nickel catalyst. It's a special metal catalyst. You could think about it like palladium on carbon, but it's not, it's nickel. And what happens is those carbon sulfur bonds are replaced by carbon hydrogen bonds. All right, that's fun. So thioacetals are formed and removed like oxygen acetals. So let's just summarize this. So when we say formed like oxygen acetals, that means that there is catalytic acid in the presence of either a thiol or a dithiol to make either the acyclic or the cyclic acetal. And then, of course, the water byproduct where that oxygen from the carbonyl leaves as water. So we formed the thioacetal from the ketone. And if you wanted, the thioacetal could be used as a protecting group. I have actually done that in my former life as a synthetic chemist. So it can be used as a protecting group. It is stable under basic conditions and perhaps a bit more stable than oxygen acetals. And then once you are done protecting the ketone, they could be removed again with catalytic acid and then water, where water will add to the carbonyl carbon and in addition elimination mechanisms, as we have previously learned, to regenerate the carbonyl and liberate two equivalents of the thiol. Okay, cool. But then today's new revelation is that thioacetals could also be reduced completely. And Raney nickel can be abbreviated like this. They can be reduced completely to generate alkanes. Okay, so they can be used as protecting groups, or they can be used to completely remove a carbonyl, replace it with a methylene. A methylene is a CH2. That's what's happened here. Now that was a lot, so we should take a moment to list the 4 different routes for reducing a ketone to an alkane, compare and contrast the methods, and write down how you would choose between them. This is a little bit like a reaction chart, but some of these transformations require more than one step. So in that way, it's more like the carbonyl grid. So there are 4 sets of conditions here. List them, compare and contrast. To ground this discussion, let me remind you that Friedel-Crafts alkylation often does not work, especially when a stable carbocation corresponding to the desired alkyl group cannot be formed. So instead, Friedel-Crafts acylation is performed, but if the acyl group is not desired in the final product, then that carbonyl must be removed. We've learned 4 methods for removing the carbonyl. The first was the way that we've really already learned before. So that is step 1, reducing to the alcohol, eliminating the alcohol to generate an alkene, and then hydrogenating that alkene. A couple of things here. If the alcohol is not consistent with E1, so if the carbocation that formed will rearrange, then E2 should be applied. And then if the molecule has an alkene in it or some other functional group that is sensitive to hydrogenation, then this method should be avoided. Now, let's just imagine there are functional groups on the ketone. And let's say this ketone has an alkene. Well, you will not be able to employ either of the methods that involve hydrogenation because the alkene will get hydrogenated. Okay, so if you want the alkene to remain intact, then there can be no hydrogenation conditions. So this will not be a suitable set of conditions. However, many types of ketones are okay for this method. It is not limited to aryl ketones. The next reduction method that we learned is called the Clemmensen reduction, and I've summarized it here. The Clemmensen reduction is a radical reaction where a metal, zinc or mercury, supplies electrons to the carbonyl and end up with an anionic species that is protonated by acid. It is only for aryl ketones, and you should avoid it if the molecule contains acid-sensitive groups. Let's imagine that, say, instead of an alkene, that the molecule contains an acetal. Okay, and you want that acetal intact, then you're not going to be able to reflux, boil, in HCl, right? So you're going to avoid Clemmensen. You might use this method that we just discussed. Well, you won't because there's acid in that as well, but you could use the E2 variant. Or you might use the Wolff-Kishner we're about to discuss, which is basic conditions, or these hydrogenation conditions, perhaps, although that might also be tricky for reasons that you can think about. So for the Clemmensen reduction, only for aryl ketones and avoid if the molecule contains acid-sensitive groups like acetals or alcohols. The next reduction that we learned is the Wolff-Kishner reaction. The Wolff-Kishner reaction occurs under basic conditions. For aryl ketones, this reaction can be conducted in one step as long as it's heated. For ketones that are aliphatic, meaning there's not an aryl group, so for example, if you had cyclohexanone, this is a two-step process. So first generate the hydrazone under imine formation conditions, so slightly acidic, and then treat it with KOH and heat to reduce the ketone. Now, you would avoid this method if the molecule contains base-sensitive groups. Now, acetals are not base sensitive, so Wolff-Kishner would be fine for acetals, but imagine there was an alkyl halide in this molecule. Well, under basic conditions, the alkyl halide would actually be eliminated, and you would generate an alkene here. Oh no, we don't want an alkene. We want to keep the alkyl halide. Okay, well, if you want the alkyl halide, then you need to avoid Wolff-Kishner. For the Raney-Nickel reaction, this is a reduction of thioacetals, and it is compatible with a wide scope of ketones, so not just aryl ketones. You first form the thioacetal. This does require some catalytic acid. And then what is super duper cool is that with Raney-Nickel and hydrogen gas, those carbon-sulfur bonds are hydrogenated right off. They are replaced with hydrogen. You would avoid this method if you had functional groups that are sensitive to hydrogenation. So basically you would avoid it for the same functional groups that you would avoid for the first method here. Okay, because it also involved a hydrogenation. So if there was an alkene, okay, so for alkenes again, we cannot hydrogenate, but you could use Wolff-Kishner. So spend some time thinking about these 4 reduction methods and when you may or may not use them, because as we discussed, acylation and then reduction is often a much more effective method than alkylation to form alkyl benzenes. And this week is all about synthesis. We can continue to build our reaction chart, and I'll just go ahead and do this for you to review and summarize this very long lesson. We learned today electrophilic aromatic substitution reactions primarily. We learned that some superelectrophile is generated under the reaction conditions. That superelectrophile reacts in an electrophile addition step. And then the hydrogen atom leaves as proton H plus in an electrophile elimination step. So these are net substitution reactions. And since the substitution is an electrophile for hydrogen, it's called electrophilic aromatic substitution. We first learned bromination. Now today we discuss these reactions only in the context of benzene, but we will learn that benzene derivatives, substituted benzene molecules, will also undergo these reactions, and we will talk about that in the next lesson. So in the bromination of benzene, a proton is substituted for bromine by treating with molecular bromine, Br2, and iron 3 bromide. And because you are responsible for the curved arrow mechanisms and understanding all of these reactions, I just will catalog for you what the active electrophile is. Okay, so for this, the benzene ring attacks bromine and breaks this bond. Chlorination proceeded by an extremely similar mechanism. Instead of Br2, molecular chlorine was used, and instead of iron 3 bromide, aluminum chloride was used to convert molecular chlorine into an excellent leaving group and generate the active electrophile. Sulfonation occurs when fuming, concentrated sulfuric acid, is added to benzene. The active electrophile is SO3H+. Nitration occurs when benzene is treated with a mixture of nitric acid and sulfuric acid. This was a pretty fun reaction because we saw sulfuric acid actually protonate nitric acid. Wow. Of course, acidity and basicity of a molecule are technically unrelated, but it was still pretty weird to see nitric acid be protonated. And eventually, that generated this active electrophile that benzene reacted with. And the real focus of the majority of the lecture really was on the Friedel-Crafts alkylation and the Friedel-Crafts acylation. And that's just because these reactions generate carbon-carbon bonds. And in thinking about organic molecules, they are made out of carbon primarily. So reactions that generate carbon-carbon bonds are often very important and the ones that we focus on. Now, what was important about the Friedel-Crafts alkylation is that it did require a stable carbocation that does not rearrange, or if it does rearrange, that rearranged cation is the one that generates the desired product. And then because there are so many limitations with the Friedel-Crafts alkylation, including the fact that the alkyl benzene is even a better nucleophile than benzene itself, and so there can be additional alkylations. This reaction is typically one that we try to avoid it when we can, and we're really careful about it. So in light of that, we discussed the Friedel-Crafts acylation, which is just a much, much more versatile reaction, or an acid chloride that corresponds to the desired acyl group in the presence of aluminum chloride does react with benzene in this net substitution reaction via this acylium ion active electrophile to which benzene adds. And then we discussed various ways that this ketone could be converted to alkyl benzenes as an alternative to the Friedel-Crafts alkylations, which have these issues. Okay, so that's where Clemmensen, Wolff-Kishner, and Raney-Nickel reductions come in. Please summarize and reflect on what you learned today, how it relates to reactions you already know, and there's many ways that what you learned does relate to previous knowledge you have. Think about what questions you have and please ask me. Consider whether or not you have achieved the learning goals so you can predict the products of electrophilic aromatic substitution reactions. Draw the complete curved arrow mechanisms for these reactions. Really, the only tricky part should be generating the super electrophile because that differs slightly from reaction to reaction. But then from that point, it's the same thing over and over, and I know that you all can do it. So the pi electrons on benzene add to the electrophile, and if you want, just keep these implied hydrogens on those two carbons that you are showing react until you have it down as second nature. Then you want to draw the two resonance structures. I'll let you do it on your own. And then finally, there's an electrophile elimination step to generate the final product, just keeping in mind that although I've written E plus twice, E plus is generic. And so in the electrophile elimination step, I really do mean that the proton is leaving, specifically the proton that is bonded to the carbon that made the bond to the electrophile. And I know it's a bit awkward that the solvent accepts the proton, but it does, so we can handle it. All right, and finally, propose synthetic routes to alkyl benzene using reduction methods. These are those four reduction methods that we discussed at the end of this video, these methods. And all you need to do now is practice. All right, let me know if you have any questions.